I have a few more problems that I would like to show you concerning trig integrals. I have those problems listed with their answers, but I thought it would be great for you to be able to see the work for these problems. They're all special, and again, they come from the section on trig integrals. For example, the first problem involves tangent to the power of 5. And there's a reduction formula for that. The next problem involves, in standard form, a power of sine times a power of cosine, and there's a table for this one. M is 3, N is 7. For number 3, tangent times secant, the exponent with secant is 3/2. In order to use the table, the exponents have to be positive integers. So we are going to use an alternative method to solve this problem, Roman numeral number 5. For problem number 4, if you notice, it's a combo of cotangent squared and secant together. For this particular problem, we will also do an alternative method. We had a table for sine and cosine. We had a table for tangent and secant, but we did not have a table for cotangent and secant. Alternative method. Finally, we have cotangent raised to the 3rd power. The section did not give the reduction formula for cotangent of x to the 3rd power. Again, I plan to use an alternative method to come up with the answer. The textbook says that you could derive your very own formula similar to the way they derived the formula for tangent x to the power of 3. But the alternative way will be much easier. In the homework exercises, you may perhaps find a reduction formula for powers of cotangent. But again, I'm going to show the alternative way. So let's begin with problem number 1. The tangent of x divided by 2 to the 5th power. First thing that comes to my mind is there's already a blue box formula for tangent to the 5th power, and there is not. So there's your problem. What we are going to do is we are going to plug into our reduction formula. I'm going to write the reduction formula down for you. And I have the formula sheet. The basic formula looks like this. Tangent of x to the power of n, and in this case we are going to let n be 5. So let me remove that. The next step, if we're going to plug into the reduction formula, I'm going to write the reduction formula down off to the side. So this is coming directly from the sheet. And I believe it would look better if I put an actual box around that. So that's the formula for n greater than or equal to 2. Before I actually plug into the formula for n equals 5, I think it would make things a little bit easier if we would be willing to change over to u. In other words, let u be x over 2, which you know is 1 half x, and du is 1 half dx. Thereby, we would need a 2 on the outside and a 1 half on the inside. Now we can change over to u, but we will have new limits. So that's tangent u to the 5th du. Our new limits will be x was 0, but now what is u? 0 over 2 is 0. X was pi over 2. Now u is going to be 1 half x, or 1 half times pi over 2, which is pi divided by 4. So now it goes from 0 to pi over 4. So make sure you do change your limits. So I'm also going to box this. Now we're ready to plug into the reduction formula. And that way it will be less messy since we went ahead and changed x over to u. So I'm going to put the overall 2 outside. And according to the formula, this is tangent of x to the 5 minus 1 over 5 minus 1 minus the antiderivative of tangent of x to the 5 minus 2 dx. I noticed I did not put a plus c. I am going to put for here 0 to pi over 4. And as a matter of fact, we will also have to put, and I guess I should have, forgive me, used u here, using the formula. Just be careful with that. We went from x to u, and then I'm using my reduction formula. Now this is the formula from the sheet, and that's why I just made my mistake, is I went back to x. I needed to keep this formula from the sheet in terms of u. You will also have to do, let's see, this tangent of 5 minus 1, tangent of u to the 5 minus 1 over 5 minus 1 from 0 to pi over 4. So we're going to simplify. That's going to be the tangent of u to the 4th over 4 from 0 to pi over 4 minus the antiderivative of tangent u cubed from 0 to pi over 4 du. Again, no plus c. This is a definite integral. So I would recommend taking, remember the 2's outside, so the 2's going to be applied to this and also this. So I'm going to go ahead and apply the 2 to the tangent of u to the 4th power divided by 4. And that's going to be 1 half tangent of u to the 4th. And remember, I'm going to go from 0 to pi over 4 minus the antiderivative of tangent u cubed from 0 to pi over 4. I need to go to my formula sheet, and there's a formula for tangent cubed. Again, this is tricky. It's in x, but when I write down the formula to finish the problem, I need to make sure this is 1 half tangent squared u minus natural log absolute value of secant u plus c. So I'm going to write this one down also, but I'm just writing from the formula sheet. I just have to remember not to use x. So that's the formula. But for tangent of u cubed, I'm going to write in, here's the blue box special for that. I'm going to write in 1 half tangent squared u minus the natural log absolute value of secant u. And I am going to remember that my 2, so let me put brackets around this, from 0 to pi over 4. And I forgot I need to distribute the 2 to this and the 2 here. So let me take a clean sheet of paper. So what I have in brackets for tangent u cubed is the formula. 1/2 tangent of u squared minus natural log absolute value of secant u. And I distributed the 2 here, which 2 times 1/4 is 1/2, and then distribute the 2 here. Since the formula has the 1/2, what I'm going to do is basically, I think I'll keep the 2 outside for the time being. So let me rewrite this. The algebra is very tricky. Okay. So that's the last step of the first page. So here we go. I'm going to deal with this situation. I'm going to say that's 1/2 tangent of pi divided by 4. And if you think about that, that's raised to the 4th power minus the tangent of 0 raised to the 4th power. So there's the substitution in for pi over 4 and then 0. Minus 2, 1/2 tangent of pi divided by 4, quantity squared, minus the natural log absolute value of secant pi divided by 4. Okay, interesting. Then I have to substitute in 0. So I am going to put parentheses, parentheses, minus, and pray that I can squeeze this in here, minus 1/2 tangent of 0 to the 4th power minus natural log absolute value of secant 0. And I barely can make another parentheses around that. So going back to this situation, this is 1/2. Tangent of pi over 4 is 1, so that's 1/4. Tangent of 0 is 0. So this first substitution just becomes 1/2. Minus 2. Okay, here we go. Tangent of pi over 4 is 1. So this is going to be 1/2 times 1 squared minus the natural log absolute value of secant pi over 4. So secant of pi over 4 is 1 over the cosine of pi over 4. And that's something you could show off to the side. I'll take an extra piece of paper here. Secant of pi over 4 is 1 over the cosine of pi over 4, which is 1 divided by the square root of 2 over 2, which is 1 times 2 over the square root of 2, which is 2 over the square root of 2. And when you rationalize that, you get 2 square roots of 2 over 2. So the secant of pi over 4 is the square root of 2. And I'm going to go back and put that here. Let me remove that. And remember, this had parentheses around it, minus, and here we go again. 1/2 times tangent of 0 to the 4th is 1/2 times 0 is 0. Minus, so let's be careful with this. 1/2 times, very careful here. If I'm not mistaken, I should have put a 2 here. Substituting into the formula. Yes. And then 1/2 times tangent of 0 squared. So go back and make that change. Minus the natural log absolute value of secant 0. So that's going to be 1/2 times 0 squared minus the natural log and I guess I need to do, let's see, minus the natural log of secant 0. Secant 0 is 1 over cosine of 0. Cosine of 0 is 1. So this is going to be the natural log absolute value of 1. And the 1/2 is basically distributed just to the 0 squared. There. And I think I underestimated how large this problem is. So this is going to be 1/2 minus 2. This is going to be 1/2 minus the natural log square root of 2 minus 1/2 times 0 is just 0. And then a negative times a negative is a positive. And the natural log of 1 is 0. So basically, all of this goes to 0. So it was this minus this. Now we can distribute the 2 if you haven't already done so. 2 times 1/2 is 1. 2 times a negative, well, negative 2 times 1/2, or let's just say minus 2 times 1/2, and then 2 times a negative natural log is minus 2 natural log square root of 2. Distribute the negative. Okay. 1/2 minus 1 is going to reduce to a negative 1/2 or simplify. And remember what this is going to be. This is the natural log square root of 2 quantity squared, because this particular coefficient can become the exponent, and the square root of 2 squared is just 2. So here's your final answer, negative 1/2 plus the natural log of 2. Obviously, I could ask for a single quotient where, you know, your denominator would be 2, so it would be negative 1 plus 2 times the natural log of 2, all divided by 2. But I think that with the difficult level of this problem, I think it's a good idea that we just say we are done. So there's your final answer for that problem. Again, that was, so what was so difficult is we had to use the reduction formula for tangent to the power of n. And in doing so, we resulted with an integral that was the tangent to the power of 3, or cubic. But thankfully, there was a blue box formula for that already, so that we didn't have to go through the reduction formula yet again. So we had to go through this with n equals 5, and it resulted with tangent of u to the third power, but there was a formula for that. And we did not have to go back to x. I stayed in u with my new limits, and in doing so, I came up with my final exact answer. Now, question number 2. I think we'll find this one to be a lot easier. The antiderivative of 7 times sine cubed times cosine to the 7th power. Okay, this is actually one of my math lab problems that a student experienced difficulty with, and I believe the student came to office hours, and we looked at the problem together. So working your My Math Lab, you may see a similar problem. I will say that I like personally that it's just x and it's not sine of x plus 5 quantity cubed or cosine of x plus 5 to the 7th power. We're just dealing with x here, and that's great. Obviously, the 7 is going to go outside. It is in standard form, so that's also good. Remember, this involves a table. M is 3 and it's odd. N is 7 and it's odd. So let's go to the table. The table says that if you have both of those odd, well, we have the situation where they're both even. We have the situation where N is odd, and we have the situation where M is odd. And so basically, you could choose to do this, follow the bullets, or you could let M follow these bullets. Both are odd. You get to make your choice. Regardless of which way you go, you will be able to prove that the answers are equivalent. They might apparently be in different forms of the final answer, but the final answers can be proven to be equivalent to each other. So I am going to use the case where M is odd. And the bullets say split off a factor of sine, apply the relevant identity, and make this particular U substitution. So I'm going to do exactly what they tell me to do step by step. Since it is just x, I don't have to worry about U substitution. I'm ready to go. So it says split off a factor of sine, and that's going to give us sine squared times the cosine of x to the 7th times sine x with respect to x. For sine squared, it said use the relevant identity. That sine squared is 1 minus cosine squared. So this is going to be 1 minus cosine squared x in parentheses times cosine of x to the 7th power times, and that's a positive sine x at this point. There you go. And it said use the relevant U sub. So I'll probably try to put that in here. U is equal to cosine of x. Du is a negative sine x dx. So we would need a negative on the inside and a negative on the outside. And this becomes negative 7, 1 minus U squared times U to the 7th du. And if it helps, trying to find a different color of pen here. I apologize. If you put a negative here and a -1 here, you can see how you change over to u. Now you will need to distribute the u to the 7th power to the 1 and to the u squared, which it becomes u to the 9th. Be careful. When you multiply like bases, you add the exponent. So 2 plus 7 is 9. And then it just falls apart from here. Obviously, that's 1/8 u, u to the 8th minus 1/10 u to the 10th plus c. And you can distribute the -7, but that's -7 over 8 cosine of x to the 8th power plus 7 over 10 cosine of x to the 10th power plus c. So there's your final answer. Much easier compared to the first problem. The only difference is they put 7/10 cosine of x to the 10th power first minus 7/8 cosine of x to the 8th power. No big deal. I guess we should know to put the higher exponent first anyway. Check. Either one is the final answer there. So that one was much, much easier, just following the bullets and doing what the table tells us to do. Now, question number 3. Oh boy, alternative method. Tangent times secant to the 3/2 power. So let's take a look at that one. Remember, the answer is 2/3 secant x to the 3/2 power plus c. You're going to be amazed at how quickly it is to find the answer to that one. So as mentioned, because the exponent on secant is to the 3/2 power, we cannot use the table where it talks about exponents m and n are positive integers. 3/2 is a fraction. Therefore, the alternative method is the following. I think it would be helpful for you to know that this is the tangent of x square root of secant x cubed. Oh, forgot my dx. Again, this is an alternative method. It's not Roman numeral number 1 or 2 or 3 or 4. It's Roman numeral number 5. The hint is you want to remember your derivatives and your antiderivatives for your 6 basic trig functions, because we can take tangent cubed and under the radical we can have secant squared times secant. Again, we're not changing the problem. We can break it up into the square root of secant squared times the square root of secant. Again, this is a product. And the square root of secant squared is just secant. So this is tangent x times secant x times the square root of secant x. Since multiplication is commutative, I am going to put the square root of secant x here, secant x here times tangent x dx. And the reason is your u is secant x and du is secant x tangent x. And that's just something we remembered from Calculus 1. And we're ready to change over to u. So this is going to be the square root of u du, which is u to the 1/2 du, which is 2/3 u to the 3/2 plus c. And then our final answer, 2/3 secant of x to the 3/2 power plus c. Final answer. Again, that was an alternative method. It was basically my knowledge that if I let u be secant x, its derivative is secant times tangent. And I used basically what they gave me as my integral. I just took a little bit of time to rewrite what they gave me. And then you can see how it quickly unfolds from there. Problem number 4. Again, another alternative method problem. There's not a table for cotangent times secant. There's a table for tangent and secant. Exponents are integers. And there's a table for sine and cosine. Exponents are integers. But this is cotangent and secant, and the answer is -1/3 cosecant 3t plus c. And I don't like working with the variable t, but when I found this problem, it came that way. So we're going to also use t. So there we go. For this particular problem, you want to think about identities. You want to think about derivatives of your trig functions, antiderivatives of your trig functions, different maybe ways to do u sub, which, by the way, with this one, you could do u sub once, and I talked about that in the previous video, or u sub twice. If you're going to do u sub twice, you're going to begin by letting u be 3t, so that you just have everything in terms of u. So cotangent u squared and secant of u. But there is a way to do the u sub once. I'm going to do the u sub once. But again, if you want to do it twice, the first thing you do is let u be 3t. So du is 3 dt. And I'm not going to go any further with that because I'm going to show u sub once. Before I do that, I'm going to rewrite by definition that cotangent is cosine of 3t squared over sine of 3t. And secant is 1 over cosine of 3t. By rewriting, you will see that a factor of cosine 3t cancels. And that's going to leave you with cosine of 3t in the numerator and sine of 3t quantity squared in the denominator. And you may say, well, that's just as complicated as what we did before, but not really. You should be able to see what your one time of u sub should be, and that is sine of 3t. The derivative of that is the derivative of the outside, which is cosine, evaluated at the inside, which is 3t, times the derivative of the inside, which is 3. And that cleans up to be 3 cosine of 3t. And then you would want to cross multiply, so du is 3 cosine 3t dt. Obviously, you would need a 3 on top and a 1/3 outside. And then what you basically have left is, and that's a 1/3, sorry about that, a 1/3 outside. You would have 1 divided by u squared du, because u is sine of 3t. Bring the u up into the numerator to make that 1/3 antiderivative u to the negative 2. And then your basic power rule, u to the negative 2 plus 1 over negative 2 plus 1. And that's going to give us a negative 1/3 u to the negative 1 plus c, which is going to be a negative 1 divided by 3u plus c, which is going to be a negative 1 divided by 3 times the sine of 3t plus c. And please don't get tempted to stop there. 1 divided by sine is cosecant. Your final answer is negative 1/3 cosecant of 3t plus c. Negative 1/3 is the coefficient, but 1 over sine is cosecant. Final answer. Again, it seems like a lot of the alternative methods are easier than some of the Roman numerals and reduction formulas and sometimes what the table tells us to do. So that was the answer to the fourth one. Now the fifth one, and then we'll end the video and then go to the video on trig sub. That one's special, and again we're going to do an alternative formula. It's the cotangent of x cubed. And here's the answer. Now, by the way, that's a blue box special. Negative 1/2 cosecant squared x minus natural log absolute value of sine x plus c. The alternative method for that is as follows. What you would like to do is break off a factor of cotangent first. So let's get started. So remember the Kit Kat bar. The whole point of that is cotangent by your Pythagorean identity is cosecant squared x minus 1 Be thinking about what you would do with u sub situation. You may be thinking that u is cosecant x, but what's the derivative of u if you're thinking u is cosecant x? You may be thinking that u is cotangent x, but what's the derivative of cotangent x? Then another thought is to distribute cotangent to both the cosecant squared and the negative 1. So you have the antiderivative of cosecant squared x cotangent x minus cotangent x dx. And then you may say, well, why don't I try breaking that up into two integrals? Because I remember Miss Manhart told me that there's a blue box special for the antiderivative of cotangent x, which if I didn't already know the blue box special, I could make cotangent cosine of x over sine of x, and do some u sub to find the blue box special. But since there's already the proof of that, the antiderivative of cotangent turns out to be natural log absolute value of sine. So the one we really have to worry about is this one. And there's probably, I would say, probably more than one way to do that one. Think about what happens if you let u be, let's say, cotangent. What's the derivative of cotangent? Also think about what would happen if you let u be cosecant. What's the derivative of cosecant? The way that I'm going to explore it, I am going to let u be cosecant x. I may go back and do it the other way also. And I think I'll go ahead here. Well, because of room, I think I'll just bring that down. So if I'm going to let u be cosecant, then du is negative cosecant x, cotangent x, dx. I would need a negative 1 on the inside and a negative 1 on the outside to change over. And that's going to be negative antiderivative of u du minus the antiderivative of cotangent x dx. The antiderivative of u is 1/2 u squared, but in this case it's a negative 1/2 u squared. And the antiderivative of cotangent x, we can now think about our blue box special. And our blue box for that is natural log absolute value of sine x. And I know what you're thinking. Miss Manhart, you said you could not have u and x in the same step. I said that you cannot have u and x in the same integral. I've integrated here, and I've integrated here. But then I have to go all the way back to x. So you cannot have u and x in the same integrand. This is u, this is x. I did nothing wrong. I integrated. Now I do need to go back and say that's negative 1/2 cosecant squared x minus the natural log absolute value of sine x plus c. So negative 1/2 cosecant squared x minus the natural log absolute value of sine x plus c. Some people may opt to say that this understood negative is the absolute value of sine x to the negative 1 power, which is 1 over the absolute value of sine x, which is the absolute value of cosecant x. So another version would be to say that this is plus the natural log absolute value of cosecant x plus c. The solution manual, when I worked this problem, left it this way. Now, another way that you could perhaps do this same problem, and I'm going to go back to my step. Maybe this is what you thought of. Here. So I have cosecant squared x, cotangent x, minus the antiderivative of cotangent x dx. So I guess you would say I'm here. Instead of letting u be cosecant x, we could try letting u be cotangent x. Okay, so u is equal to cotangent x, and its derivative is a negative cosecant squared x, and then you have the dx. I'm going to put a negative on the outside and the inside with a little bit of rearranging. And this becomes negative antiderivative of u, and a negative cosecant squared x dx is du, minus the antiderivative of cotangent x dx. And I believe we end up in the same place. This is going to be a negative 1/2 u squared minus the natural log absolute value of sine x. And u is cotangent. Make sure I did this correctly. So negative 1/2 cotangent of x squared minus the natural log absolute value of sine x plus c. Well, before we got negative 1/2 cosecant squared x minus natural log of sine x plus c. And this time, let me put them side by side. Because I attempted to do it two different ways, unless one of my ways would happen to be absolutely wrong. Or could I possibly prove that those two are equivalent? So that's what I'm going to attempt to do. Either one would be fine as your final answer. And I would just know that some students would let u be cosecant x, and other students would say, well, let u be cotangent x. I am going to take the one that we just received, negative 1/2 cotangent squared x minus the natural log absolute value of sine x plus c, and I'm going to prove that it's equal to negative 1/2 cosecant squared x minus the natural log of sine x plus c. It's really simple. In place of cotangent squared, I'm going to put its identity. Now the identity is cotangent squared x plus 1 equals cosecant squared x. Therefore, in place of cotangent squared x, I have cosecant squared x minus 1. Again, if you have forgotten, cotangent squared x plus 1 equals cosecant squared x. So if I subtract 1 from each side, cotangent squared x is equivalent. And this is the beautiful part of it. I'm going to go back and add a sub 1, and you'll see why in just a second. Let's distribute the negative 1/2. Make it a c sub 1. And then addition is commutative. So I'm going to say, obviously, addition is commutative. Negative 1/2 cosecant squared x minus natural log absolute value of sine x plus 1/2 plus c1. Well, guess what? Any real number c sub 1 plus a real number 1/2 is yet still another real number. So your final answer is this. If we let capital C be 1/2 plus c sub 1 for any real number C sub 1. And that is the proof that the two answers are algebraically equivalent. And I believe that's the last problem. So I'm going to conclude this video. I wanted to talk a little bit about trig substitutions in the next video. But I hope you will have an opportunity to go back and practice some of these problems on your own. I apologize if the video is blurry at times and the volume's too loud or too low, but there's no perfection in this. This is just me, an amateur video maker, I guess you could say. But my heart is in it. I really wish for you to learn with these extra examples, but you have to do these on your own also. So please do try these. You know the answers. And you know me. I can change a few numbers here and there, but you could possibly see one of these problems on a test or a quiz. So God bless.